This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is a heat pump. In this example, we're given that there's 50 kilowatts required to heat the building. And the heat is going to go into the building, 50 kilowatts. And the heat pump is operated by input heat, and the heat pump absorbs heat from the air, and together they combine to make the heat that is useful for the building. Now we're told that the seller promises a coefficient of performance of 3.5. And under those conditions, we're going to look for the power to run the heat pump, and we're going to look for the cost to operate it for a day. All right, the information we need to get started is the coefficient of performance. That's this value here, coefficient of performance. And they're different for a heat pump and for a refrigerator. For a heat pump, it's the heat out divided by the work in. Now the units for this thing are joules divided by joules. And if we take that and multiply by 1 over seconds, we're going to get watts divided by watts, because the units that we're given here is W dot up above. Up here is W dot. And here is, this should be a Q dot. There's a dot that should be there. And a dot that should be here. So that we're going to use heat rate. We're going to use gamma in the form of heat rate, Q dot out, divided by work rate, W dot in. Because that's the value that we've got. Okay, we can rearrange that. Rearrange. We're going to have W dot in that we're looking for equals Q dot out divided by the coefficient of performance, and we can compute that be our 50 kilowatts divided by our 3.5 coefficient of performance, and we get 14.3 kilowatts is the rate of work required. That takes care of part A. Part B says, what's the cost? Well, we've got $0.09 per kilowatt hour. Kilowatt hour is a rate of is an amount of energy. We're going to multiply that by kilowatts. And then we need our day. Let me put in 24 hours per day. Then the hours are going to cancel. The kilowatts are going to cancel. And all we're going to have is dollars per day. 0.09 times 14.3 times 24 is $30.89 per day. Let me add a part C and think about, suppose the gamma value was 1. This is the lowest possible. And in the situation of gamma equals 1, what happens is the definition says gamma equals Q dot over W dot. We're thinking of the dotted version. Pull that down, and I have that in the case of gamma equals 1, we have W dot in exactly equal to Q dot out. And looking at the picture up here, that would say that all of the energy that comes in goes out, and there isn't any effect of the air. So this would be no better than an electric heater where the power is converted to heat and heats the building. This situation can occur because the coefficient of performance goes down as the air temperature, in this case for an air-linked heat pump as this is, as the air temperature goes down. So that any heat pump system needs a backup system, a backup heater, I'll say, for very cold days. I'll say on very cold days. And the situation of the backup heater is something like less than 20F. All right, let me recap. We're given a heat pump. We're told we have a certain amount of heat, and that's the stuff that goes in to heat the building. The power comes from understanding the coefficient of performance, which we rearranged and converted to a rate version of the coefficient of performance. And we can use the cost to find the cost per day if we follow the units carefully. And if you remember that every heat pump has a descending coefficient of performance as the temperature of the heat source, in this case air, also descends, then all will be well.